Good afternoon, good morning, ladies and gentlemen. My name is Łukasz Głacz and I am happy to present to you a solution to the task number 40, titled Moving Cylinder. Let me remind you the content of the problem. Place a sheet of paper on a horizontal table and put a cylindrical object, for example pencil, on the paper. Pull the paper out. Observe and investigate the motion of the cylinder until it comes to rest. During our presentation, we will at first focus on a cylinder that will be moving on a line. The cylinder will be placed this way and the paper will be put like this. At first we show our theory for this situation, we derive some conclusion and compare them with experimental results. Later on we move to the full model when the cylinder is not placed like this, it is rotated and the paper is pulled this way. We present theory on the basis of which we build a simulation and we will compare the results from simulation with those from experiments. So at first I would like to talk about motion along the line. In this case we have a cylinder placed on a sheet of paper, placed on a table. We will assume that cylinder, table and sheet of paper are rigid bodies. We will also assume that paper is pulled out with constant acceleration A. We can then write forces acting on the cylinder. Those are reaction of the surface force, gravity force, and friction force. Making use of Newton's second law, we can write equations of motion for our cylinder. Unfortunately, we cannot solve this system of equations until we know something about friction. In our presentation, we focus on static friction and dynamic friction. Static friction occurs when is a friction that occurs between two surfaces when there's no movement between them. And dynamic friction is friction which occurs when the movement exists. Knowing something more about friction force, we are able to add new equations to our system. This equation represents that there's no movement between cylinder, point of contact between the cylinder and the paper. And this equation tells us that for dynamic friction, the value of friction force is constant, equal to mass times gravity times coefficient of friction between surfaces. We can also find a critical acceleration which tells us when we talk about static friction or dynamic friction. By solving this equation of system, we can derive many conclusions. For example, if we assume that initially linear and angular velocity of our cylinder is 0, then the ratio between angular and linear velocity stays constant, independent of type of friction or friction coefficient. And it's equal to mass times radius of the cylinder divided by moment of inertia due to symmetry axis. Knowing this, we can show that when the paper is pulled out, the linear and angular velocity becomes 0 at the same time. When the cylinder comes to rest, it also loses its angular velocity. We will define two parameters. First is d1, which is distance from the cylinder to the end of the paper, and second parameter, which is d2, and its distance from the point of first contact to the point of full stop of the cylinder. We can show that for static friction on the paper, the following relation holds, and for kinetic friction, following relation holds. For exemplary values for use by us cylinder, we can show this story on a plot. Here you can see the ratio between d1 and d2 and d1 in dependence on acceleration of the paper. In order to check if this is right, we've built a following experimental setup. In order to achieve constant acceleration of the paper, we attach the paper with line to pallets and attach some weights. By increasing weight, we could achieve greater acceleration. And pallets were used for us so we can achieve acceleration greater than gravitational acceleration. In our experiments, we used two materials. The first is paper, which coefficient of friction between paper and cylinder was measured by us, and fabric with following coefficient of friction. In our experiments, we used metal cylinder, as you can see here, filled with plasticine, and attached bright LED. In order to measure the acceleration, we used a flashing LED, whose flashing frequency was controlled by microprocessor. Here you can see this flashing green LED. The experiments were made in the following way. Paper was pulled away, cylinder was placed on the paper, and paper was let to go. We could see the motion of the cylinder. By taking long exposure photos of this setup, we could arrive with the following picture. Here you can see moving cylinder, and here you can see this flashing green diode, which tells us what is the acceleration of the paper when we actually measure length of those lines. By taking a closer look at our cylinder, we notice that there's a different reflection when the cylinder is on the paper and when that cylinder is on the table, because we can precisely find the moment when the reflection changes. This is exact point when the cylinder touches the table for the first time. Thanks to this, we can precisely measure the moment when the cylinder touched the ground for the first time and measure this distance. This distance traveled on the table. By comparing experimental results with theoretical prediction, we find a good agreement. These experimental results are for the paper, and you can see that we find an agreement here, and we also ran some experiments for fabric. We also found a great agreement. We also tried to look at the ratio between angular and linear velocity. If it is constant, we can show that the point of the cylinder will move on creating a shape called cycloid, which is shown over here. In order to check if this is right, we attach another green LED to off-axis to our cylinder, and we also again took long exposure photos of our set. We arrived with following photos. If we compare this with our theoretical prediction, we find a great agreement. Theory fits this curve. And maybe this is not readable, so I will read it. It is very important that this curve is not changed, whether the cylinder is on the paper or on the table. This means that the ratio between angular and linear velocity is not changed. Now I would like to move to the cylinder, which is not placed so friendly on our paper. The cylinder is placed this way, and the paper is pulled like this. This situation tends to be much more complicated, and in order to explain what happens, I first focus on a block, on a rectangular block, on a base which is escaping this direction. We can show that if we assume this simple rigid body model, and we assume that friction force is right below the mass of center, we can show that there's a torque acting on our block. Because the torque is non-zero, this indicates that there will be rotation of the block. As we know from everyday experiment, this is not always the case. So the simple rigid body model is not enough. We need to talk about distribution of reaction force along the surface of our block and we would need to calculate the torque as an integral over this distribution. And in order for there to be no rotation and no detachment from the paper, we will demand the torque to be zero at all time. So, if we have a cylinder placed on our paper and paper is pulled out this direction, we can show that reaction force will be higher at this point, which is farther, and reaction force will be lower here. Because this is complicated, it is quite complicated to find a full distribution of reaction force. We will assume that there are two reaction forces placed evenly from the center of mass. We can calculate those forces using only rigid body dynamics, and we don't need a full theory of elasticity. In order to find what happens with such a cylinder, we introduce a new frame of reference, which E1, E2, E3. In this new frame of reference, E3 is always equal to Z, and and we will assume that there's no rotation around E1 axis, so the cylinder will not detach from the paper. In this, we can write equations of system in this new frame of reference for mass of center motion and for rotation of our cylinder. The first equation is center of mass motion. This equation demands that there's no detachment from the surface, and those two equations are equations of motion of our cylinder. By simulating those equations, we can find that this is interesting result, that angle, this alpha here, will change, and it will decrease like this way during when we pull the paper out. The angle will go to 0, so the cylinder would like simply to roll. This is shown here by this animation. Okay, you can see that this is what I said. The cylinder will rotate so it can roll. In our experiments, we see that this is the case. Here are photos from our. We perform a experiment recording it with high-speed camera, and you can see that cylinder actually rotates. It rotates so it will simply roll on this paper. We compared, by analyzing this video, we could compare experimental results with theoretical prediction. We find a great agreement here until the cylinder left the paper. So, the main reasons for error are is that the coefficient of friction varies over the surface. There's difference between static and dynamic coefficient of friction. Okay, so I only summarize quickly. Ratio between linear and angular velocity remains same, independent from parameters such as coefficient of friction or friction type. Reaction model gives results comparable with experiment. We have built a simulation that allows us to predict cylinder's motion. Cylinder in 3D situation tends to change its orientation in such a way that it simply rolls on the paper. Here's our literature. Thank you for your attention.
I have some questions for the report. During your report, you said about there are two kinds of friction force: static friction and dynamic friction.
Yes.
Yes. You said the equation, show the equation to show the border between them. But numerically, how much is it for your cylinder using it?
It was. You can see this on the plot. It was about 4.5 meters per second square.
4.5 meters per second. Okay, thank you.
Yes, for the paper, you can see
well,
it's actually 3.5.
Well, in all your experiments you made while pulling the cylinder without putting it under angle, it was always stopped in your experiments. There was
not always. We can discuss it in the discussion.
Okay, I agree with you. We will discuss it.
So there will be no rotation. We'll try to.
Well, okay. How did you measure friction coefficients?
Friction coefficient was measured in an experiment. We have a cylinder on a table on this material.
Okay,
and there are weights. Yes, and we change the orientation of the table.
Okay.
And we look at when it moves.
Okay, and don't you think then in the different direction for the cylinder can be different friction forces? For example, if it has some structure, some sharp structure on the surface, can it be different in different directions?
Can it be different in different directions?
Or use good material on the surface?
No, as we observed, there was no specific difference.
Okay, I'll now prepare my speech. Thank you. Good morning, our respectable jury, team arrivals, reporter, and reviewer. I'm reporting co-representative of Belarusian team, and I'm going to make an opposition to the problem moving cylinder. You all heard formulation of the problem from the reporter, so I wouldn't remind it. Well, let's go first to the points of the report. There was lots of positive points, such as structure of the report. We exactly knew what we are going to hear about during the report, and there was no problem in understanding. There was different orientation of cylinder on the surface, which also included a very complicated motion. And I think that it's really nice because it wouldn't be a full solution if there would be only one perpendicular orientation. There was, again, theoretical explanation for both the motion. It was really fully explained, but it's, I think reporter should pay a bit more attention to their development of the formulas because it wasn't clear enough to hear. Well, there was high quality experiments. We saw a video captured on high speed cam and also light diets or something like that, as far as I understood. And they proved their theory by their experiments. As we saw, it was really nice. And they also took different surfaces, so they, I think, there was no shown that in their experiments because I think there would be the same motion, though it's okay. There was also trying to estimate the charges. Sorry for this. The negative is the energy point of the problem because, there is always working on energy, law of energy conservation, and there was nothing said about it. It was just a dynamics. Maybe their point of energy would let us to understand the problem a bit deeper and wider. They estimated, the reporter estimated errors, but into his errors he didn't include an ideality of cylinder. I don't think that the cylinder, handmade or even some another cylinder, can be really perfect and didn't cause some errors. There was no full observation of the motion under putting of cylinder under angle, because there was observed only the changing on the angle on the surface of the paper and nothing after detaching. Because if it would detach, I think there would be a really interesting kind of motion, and reporter didn't use it. And now I'm going to go to discussion. I'm sorry, can you? You'd better put into your laptop because I would like to ask something about your slides. Possibly. Okay. Oh, I want to take this place. Okay.
Низкая новизна. Низкая новизна.
Okay. First, I wanted to say something about your experiments. They were really nice and great, but I noticed one interesting fact. Yes. Can you please show your picture of light pointing to the cylinder? Yes, like this. Yes. You may see the oscillations.
Yes.
And what is causing it?
First of all, it's really hard to place our LED perfectly in its center. So it will create like small cycloid, which was discussed later. Okay. But if we place it directly in the center, those oscillations disappear. It depends. In some experiments, it was smaller, larger, but it doesn't indicate
and
the
if we move your laser pointer, there has another density than all other cylinder. So it may cause the misdirection. There are some jumps, and could it cause some experiments?
Excuse me, could you repeat?
You have a cylinder of constant density, and you put in, for example, a constant.
Okay.
And you put in some object not in the center with another density, and it causes deflection of the mass center.
You mean about plasticine or the LED?
Your laser pointer.
LED.
LED. This LED. Okay. the mass of our this pointer, as you name it, is really small in comparison to our cylinder. The cylinder weighs about 250 grams, LED weighs about 5 grams, and it's totally different. And it's almost
there is not the problem of the changing of mass; it's a problem changing of density. You could the cylinder can be more densened in some certain point, and that's why the mass center would be deflected, and your cylinder will go something like jumps.
Like jumps, they were not observed.
Well, okay, this is just a pointing of
this is laser project. It's very hard to break it in the center. Second, its orientation can change.
We got here on the opinion. Okay, this is for what exactly motion? This picture.
This is
motion
for
with static or
static, with static friction on the paper.
Static friction.
Yes, we experiment with different types of friction, different acceleration. This particular picture is for static friction.
Okay, and well, is there any qualitative difference between static and dynamic frictions? Well, as you said in the report, the ratio would be the same for both kinds.
Yes. Yes.
Okay, and
ratio is the same. And first of all, the way the qualitative difference, the physical difference when you have a kinetic friction, is that cylinder point of contact will move on this surface, like it will rotate.
Yes.
There will be movement between the surface and the point of contact. In case of static friction, there will be no movement.
And well, in case of static friction, we should also take into account rolling friction, as far as I understand.
Rolling friction, we tried to assume the rolling friction for our cylinder, and we found it to be negligibly small.
Well, okay, but if we decrease our acceleration of paper, and your rolling friction start to be really great, comparison with the friction forces acting by their paper.
We run experiments for low accelerations. You can see here, and
it's for low acceleration.
Low acceleration. Here we have acceleration lower than 1 meter per second, even lower than 0.5 meter per second squared, and you still find a great agreement between theory, including only static friction, not including rolling friction. So even if we look at this, those points almost match the theoretical curve. So this is another proof for the rolling friction to be negligibly small.
And and if we decrease your acceleration a bit more, can it be cited that the rolling friction will cause some another effect?
If the acceleration would be really small, yes, I agree, it could be. But we focus on those. We didn't focus on those really small, because the problem is really interesting. If we take this wide range from 0 to 10 meters per second squared, it's quite a wide range. And it was,
I think at this point your point observed perfectly. But let's speak about the cases which could also be to make some wider understanding of the problem. What motion can be caused by the low acceleration of paper by the rolling? Would the rolling somehow affect their quality? Would it stop in the end, or should it roll forward or back?
Okay, if the cylinder is perfectly perpendicular to the direction of pulling, and and we assume that it doesn't change its orientation here,
yes, okay,
it will come to the full stop. But in our experiments, we also observed that the cylinder is if it falls from the paper, this is a very hard problem to find the theory for this. But if it falls from the paper unevenly, there's different coefficient of friction, there's different movement.
So it's trying to
turn. The surface it tries to turn, and this may cause rotation of that cylinder. In our experiments here, we tried to make the experiment in such a way that the cylinder actually comes to full stop this way, so it indicates this Bondara effect was negligible.
Okay, so you try, do experiments need great accuracy to make it?
Accuracy in terms of...
how repeatable are your experiments? If I try to do the same experiment by hand, how successful will be I?
I think it will be very successful. And
that's nice.
And you can, on this graph, you can find actually some disagreement about here. And this is the point where these experiments are not so repeatable, because for low acceleration, this is a very nice observation that for low accelerations, it was easy to make a cylinder fall. way that was easy
Okay,
to navigate. For high acceleration, it was also, but for this acceleration in the middle, there were many times the cylinder was deflecting from its direction.
I think it's a very nice point you told about it quite well. You didn't pay attention to it during the report, but
okay,
I think it's good that we come to this in the discussion.
Yes.
Well, also you spoke about their movement on the cylinder on their when it plates under angle, and you didn't say anything about its motion on the surface, because you showed the angle if their length of our paper is infinity. And when I have such a paper, a usual paper, you see, yes, like you, and you will place it under angle and pull. How would it move on the surface? Okay, theoretical research.
How it moves on the surface?
Yes.
You mean the angle will change and the motion?
Well, yes.
Okay. The center of mass will move. Like I put it this way, it will.
Well, if we take a very small distance, that
this
way almost wouldn't change the angle.
It wouldn't change the angle. Also, if the acceleration is high, the center of mass wouldn't move much. Because if you pull it very fast, the center of mass wouldn't change much. But if you pull it slowly and the paper is infinite, the center of mass would also
you
move.
spoke about infinite pulling, but I mean, when you have such a pulling, well, just experiment like that.
Yes.
How it goes on the surface. Here I saw it's rolling, and that gives some experimental.
Yes, it's rolling. It changes its angle a bit. It's
I think the most interesting point here is when it's on the border between surfaces.
You're asking about what happens at the border.
Yes, on the border and on the surface.
Okay. Theoretically, it's hard to describe it because
everything changes in each moment of time.
Yes. You need to write a simulation. You can you cannot then assume it's a rigid body. Even this reaction force will not fit. You need to calculate the whole reaction distribution.
Can you qualitatively say how it will be?
It could rotate and begin to rotate this way. Rotate. This is what we observed in our experiments, but this is in order to compare this with theory, it's very hard, and we focused on what happens on the paper. We built a simulation which allows us to tell it.
You focused on the part of the problem you can explain by math.
No. And yes. And second thing is that our simulation allows us to tell what happens with the cylinder on the table when it has an angular velocity. So we only miss the part with the cylinder on the border when it's half here, half here.
I also had a question. Did you try to change the direction of pulling of your paper? If we try to direct it up, for example, what is going to be observed?
If you pull it at the angle, yes?
Yes.
Okay, the problem there becomes more a bit more complex in the 2D, this motion of the line.
Yes, and
you can find easily. You can qualitatively. It will behave in a similar way, but you gain another force. Force of gravity is this way. Reaction force is the other way, and
so it will cause an additional acceleration.
Yeah, there's actually not additional, but direction of reaction force will change.
Yes, and so it has a horizontal projection, so we have another acceleration.
Yes, you might think about it that way.
Okay, thank you for a great discussion.
Yes.
I really liked it. Thank you for more deep understanding. Well, it's yours.
I liked it. Questions?
Okay, yes, I have a question to both of you. What would actually happen if you would take another cylinder, like for example a hollow one? Would it be faster or slower than a full cylinder? To the recorded system?
Okay, if we take out the plasticity, you mean, yes?
Yes, for example.
Yes, the moment of inertia of our cylinder will change. And the whole motion will be a bit different. You would see that in our theoretical examination, we included the moment of inertia.
So will it be faster or slower?
What do you mean by faster and slower?
Velocity of the cylinder.
It at which moment. Like it's on the paper, if there is static friction, it will behave the same.
Well, I think that, there is, as I said, that it's not good that reporter didn't took into account energy, so by the energy it should have the same energy if we don't change math. So, and the total velocity will be lower because the moment of inertia is bigger.
Okay, thank you. Yeah, what would happen if you would pull the paper out at an angle?
At an angle,
Yes.
like I presented in my students. Oh,
No,
you mean the
upwards,
paper
for
at the
example.
angle? Yes. No, it's a situation very similar to a situation when we have a cylinder at the angle, because if you look from the paper for the cylinder, the paper is on the angle. Only if
No,
you
I mean
goes
if you pull the paper out upwards, for example.
upwards. Like you have it was I think explained in the discussion that there are the theoretical model should be a bit different because reaction force changes its orientation. The cylinder itself, without pulling the paper out, will roll on the surface down. So it's like a bit a different program.
Okay.
And
To the opponent, you were not convinced by the little LED lights. Do you have a proposition how to improve that?
Improve what? Direction of, about this plot, yes? About the oscillations, or yes? Well, I don't know, maybe, really it should be pointed somewhere in center, but I really don't know how to increase the accuracy. Because as we see, the oscillations are very small, really small. And we don't observe the high static oscillations just by they have the same phase as the oscillations of the whole cylinder. So it's just their deflection. We should just increase somehow their way we put in their pointer.
Okay. And one more question to your forces. Can you maybe show the
forces acting on the cylinder at the angle or perpendicular?
or just the reaction force? Do you have what forces do you have pointing upwards?
At the beginning, yes, here. Here, this light, it's the reaction of the surface of this paper. Those are forces acting on our cylinder only.
Thank you very much.
Here.
Goodbye.
Что-то и оператор, и калькулятор. Подожди, а где мы вот? А, кстати, где можно забрать? Что тебе не нравится? Ну, он рассматривал, молодец. Вот такое? Он сказал, что там будет 3 этих степени свободы. То есть он фактически все на самом деле рассмотрел. То есть, если он захотел, он бы записал все результирующие, потому что он записал энергии. Насколько я понял, это были энергии. Но походу это было какая-то хуйня, потому что она обозначалась буквой Г.
Г это момент у него был.
Г?
Да.
Но он имел размерность энергии.
Момент.
Там было и омега-омега.
Это, кстати, dl по dt. Это момент.
dl или dg?
dl по dt равно dg. Вот просто г. Это момент.
dl. Момент силы. Забавно. Смешно. Гусеничка. Так, на плане не могут вызвать? На плане не могут вызвать?
Нет, ты не можешь сыграть, не сыграть.
Я зайду курить. Иду на диван, заберу сигарету и буду курить. Может быть, согласен. У них теперь просто поддержка.
Не забывай, возможно, ты зарегистрировался на один скиннер.
Ну что, не проблема. Что? Ты чё? Они ни хрена ничего сыграли?
did a lot of experiments, and you nicely described the motion of the cylinder until it came to a rest. You showed us that both the rotation and the translation stop at the same time, and you also said that there were two phases, like the cylinder on the paper and the cylinder on the table. And you showed us the dependency between the angular frequency and the velocity. Now to your weaknesses, I thought there were many parameters missing, as for example, if the mass has any effect, or if you take different materials from the cylinder, or pulling out the paper, for example, at an angle. And there were also experiments missing for this. And it wasn't clear when that you have static friction and when that you have dynamic friction. So I think it is important to know that on the paper probably there is no dynamic friction, but when it hits the table, you have dynamic friction. I would clearly differ between these two parts. And the dependency between the velocity is missing. I mean, it is really clearly dependent on the moment of inertia. So it was not clear in the conclusion maybe that the velocity is really dependent on that. And you used irrelevant materials. I mean, in the problem it says you have to use a sheet of paper, so the experiment with the material was not really necessary. To the opponent, your strengths, you asked relevant questions. You had the measurement of, the coefficient of friction, and you also talked about different frictions. You used additional parameters, like, for example, pulling out the paper at an angle, what he didn't mention that I thought was good. But some weaknesses were that you somehow didn't really focus on the relevant things that were missing. And, for example, you could have gone deeper into physics. And what I liked about your discussion is that you really, you talked about the LED lamp, you talked about pulling the paper out, you covered many different aspects. And so to your discussion, generally, I thought good. I thought you brought really a lot of parameters. You brought static friction, dynamic friction, rolling friction, and as well the angle. And it was good. You didn't stick just to one point. You nicely moved on. You discussed the accuracy of the experiments that I thought was very interesting, and you found the important lacks, for example, like the change of the mass distribution with the LED lamp. What you didn't discuss were many parameters, like the radius. For example, if you have two cylinders with the same density, if somehow the velocity changes if you change the radius, if it is dependent on the radius at all, or of the length of the cylinder. I think these dependencies were really not clearly covered, neither in the presentation nor in the discussion. And at this point, I want to thank you very much.
Okay, so at first I would like to thank all the reviewer for great for summing up the presentation. I would like to thank you once again for a great discussion, and I would like to mention at first some aspects that I think are important, and I mentioned, and it was not clearly understood by the author. Here, for example, it was said that I didn't discuss the dependency on parameters such as radius, moment of inertia. It is discussed in a theoretical part. We take these parameters into account, but it's hard to investigate every single relevant parameter. We decided to investigate how the situation changes when we change the coefficient of friction. This is done by using different material. Here you can see the fabric we used. Here you can see paper we used. I also see no point in discussing no very important. I don't see an important point in discussing the energy of the system. It is this approach. It's very similar to approach with forces. Like from force, we find forces, we use second Newton's law, we find the coefficients of motion. Similar with energy. We have energy, we calculate the energy of the system, we calculate the Lagrangian, and then we find equations of motion. It is a really similar approach. And I would like to, now I would like, when I clarify those points, I would like to especially thank people who helped us during this presentation. I would like to thank Professor Czesław Bayer for focusing our attention on this two-reaction model, which allowed us to create this simulation for this non-ideal case where the cylinder is under angle. Already? 2 minutes? Oh, okay. So I would like to thank you for your attention. Okay. So that's it. Questions from jury, yes? Seven, yes. And this at the moment. Yes, here's slide 7.
Right. So I suppose the diagram below is the direction in which the cylinder will be rolling, right?
Yes.
Rolling towards our right.
It will roll this way. It will move this direction and roll
Right.
this way.
You're going towards our right.
The cylinder is going right and the roll is this way because paper.
So can you tell me what is the T on top?
T is friction force. Due to the motion of this paper in this
So
direction.
the paper is pulled rightward.
It's pulled right way, yes.
Okay.
This way. I put the paper this way.
The opponent, what do you think T is?
I think that's all right here, and the friction force should move the center of mass in the same direction with the paper and roll its, like it should roll on the surface.
But this friction is acting on the cylinder, am I right?
Yes, there is, of course.
Okay, the reviewer, what do you think it is?
I think it is. So I think it is in the other direction.
You think T should be in the opposite direction?
No.
One question to the reporter. On slide number 22, can you briefly explain how your error analysis is done?
Here, yes, okay. We prepared, we ran some, when the initial conditions were specified, like for one situation, we pulled the paper many times, and we calculated this, it was about 30 times. We pulled the paper out, and we found what were the results, and we calculated the standard deviation of those parameters, and we then assumed that it is, of course, an assumption that it is similar for every case. It is like we calculated this deviation for this critical moment. It's for 2 points, for 3 and for 6, and the standard deviation is our error.
Okay, thank you.
What is the effect of the velocity of moving the paper?
Velocity.
The showed that the cylinder doesn't move.
Okay, we focus on acceleration because this is a critical parameter which describes the way. Is it a static or a dynamic friction on the paper? If we pull it with constant velocity, like at first we have an impulse, like a high acceleration, so then the situation is more complex because at the beginning we have high acceleration and dynamic friction. This dynamic friction changes into static friction at some point, but we focus on the acceleration of the paper. Did I answer? Yes.
And do you have any idea? Could you tell me why the cylinder stops finally? What is the process?
Because when we are on the paper, the friction forces act on the cylinder is directed in the direction of pulling, and when the cylinder is on the table, the reaction force direction changes, as it is shown here. This is the force acting on that cylinder, right? At first it is one direction, and when it falls on the table, it's opposite direction. So both center of mass motion changes and the velocity, rolling, this angular velocity changes.
Why the direction changes?
Excuse me? Because at first it is on the paper. Paper is pulled that direction. So the force, friction force acting on the cylinder is pointed that direction. But when it is on the table, it moves and it rolls, but the surface does not roll. So the friction, the movement of the velocity, the velocity between the cylinder and the surface at one point is positive, and when it hits the ground, it's negative. It's like the movement is between point of contact and the surface is different. When it's on the paper is pulled this direction, so the cylinder move this way. It would it stands. So when it moves, there's force that acts on the cylinder, so it rolls. But when it rolls and it falls on the table, it rolls this way, and the surface doesn't move. So it tends to stop.
Announcing the points for the reporter.
Would you please tell the point?
Okay, 7, 6, 4, 5, 9, 6. Okay. 6. 9, 6. 8 or 9?
The reporter.
No, it's still report.
Reporter. So for the reporter.
Last.
To the reporter.
7, 6, 4, 5, 8, 6. Last edition. And for the opponent? Five, 6, 6, 7, 9, 7. And finally for the reviewer. 5, 5, 6, 8, 9, 9.
It's time to break.
Did you ask for explanation because there are high and low grades? Yes.
Yes, the single highest and single lowest grade. You need to tell how they move.
Бывают такие случаи.
Exactly. So for the reporter, I have a 0 in the section of the report. So the report was, or the section reporter. Some formulas were not introduced clearly to my way, which is the point of the scoring guidelines. And on the other hand, we saw a live demonstration, which I really liked. So this is a 0 in all. For the presentation, I have minus 0.5 because in the end, time management did not work out. And there were some missing dimensions. For example, in where you showed us the figure tracking, no dimensions were given. And to my point of view, we haven't seen any scale at all. And to my opinion, the presentation is always too fast. Went too fast over your formulas. And coming to physics, I have another minus 0.5 because you didn't consider the case of slip ring between a cylinder and a paper. And you showed us some basic formulas, but what I really missed was a systematic variation of parameters.
about the grade 5 problem, I guess, from the respected chairman, just maybe for us to improve our Twitter performance. I'm asking about your grade for our opposition, if it's possible. No, what?
Нет, 5 минут поставь. 5 минут поставь. Пистол 9. Пистол 9. Да. 5 пистол 9.
In short answer, to add more points, I couldn't find any